Hi folks, welcome to another YouTube live review for Calculus 1. We're going to start with optimization for a couple problems and then we're going to get into Riemann integrals and the definite integral today. So without further ado, let's get started, and as always there's a question or chat box over on one side of your screen. Feel free, if you have any questions, please ask them there and I will answer them as soon as they pop up in the chat box there. So we're going to begin with finding the maximum area of a triangle formed in the first quadrant by the x-axis, the y-axis, and a tangent line to the graph f of x equals x plus 7 to the negative 2 power. So let's take a look as to what this is. So first off, this is f of x equals, another way to write this is 1 over x plus 7 the quantity squared. And if you're looking for the graph, it just basically shifted the graph of 1 over x squared to the left 7 units. So you get something that looks, well, technically, if you want to draw out the full graph, you get something like this. And then the graph goes something like that there. Now, to give you a bigger picture as to what we're doing, we're basically taking some tangent line. So maybe the tangent goes right there and right over here, and we form a triangle. Now notice this is a right triangle here, but so we have this little triangle sitting right here, and we want to figure out maximum area. So the maximum area of that triangle. Okay, so in order to do this, what do we need to do? Well, we need to figure out how the heck do we get a couple values. And so the first value will be this point right here. Not saying it's actually on the curve. It's not necessarily on the curve. I drew that a little bit bigger than what it should have been. But so you have a point 0, let's say h, and let's say this point is b comma 0, right? So what we want to do is maximize this area, which is the area equation. So we'll put area of a triangle is 1/2, and since we labeled them b and h, there was a reason for that. It's 1/2 base times height, right? And our b and h are corresponding to that. Okay, so we need to figure out a way to get the b and a way to get the h. So we can't have two variables involved when we take our derivatives in trying to optimize. So we got to try and fix that. And actually what we'll do is we'll introduce a new variable to try and do this, because the only information that we have is we have the curve, right? This 1 over x plus 7 squared. And then so that means that there's some point where we're going to take this tangent line in a minute. So this is 1 over, or c, and then 1 over c plus 7 squared should be a point on that graph that we're going to find the tangent line for. So in order for us to find a tangent line, we need to find the slope of the tangent line. So that's what we're going to start with. So we're going to find the slope of the tangent line. And as always, if you get lost in the process, please let me know. There's a place where you can ask questions right there, so just kind of tell me about it. So in order to do this, we need to find f prime of x. So you have the function. A nice way to write it is this way. We'll need to use the chain rule, but first, in order to use that chain rule, we're going to use the power rule. So you get negative 2 x plus 7, and then it goes to the negative 2 minus 1, which is negative 3 up top, and then times the derivative of the interior function, which is just a derivative of x plus 7 is just 1. Okay, so an easier way for us to write this then is just negative 2 over x plus 7 the quantity cubed. Now the reason I'm writing it in actually this format, we would probably want to simplify in this sort of problem, just because there's going to be all sorts of nasty bits and pieces. So in order to work with this, we have this point c, and I'll go back to the blue here. We have this point right up here, c1 plus c1 over the quantity c plus 7 squared. So we want to use that c, so we're going to go f prime of c and figure out what that would equal. Well, it would be negative 2 over c plus 7 the quantity cubed, right? Okay, well if that's the case, then this should be the slope at x equals c. And I should write slope of tangent line, but we write find slope of tangent line, so hopefully you get the gist there. So now what that means is we can use the point slope formula. You get y minus our y1, which is 1 over c plus 7, the quantity squared. You might ask where I got that from. Once again, and go back up to that original point, equals m, which is our slope at x equals c, so this should be negative 2 over c plus 7, the quantity cubed. And then we have x minus c. Alright? So now, using this, can we actually work with this to find our b and our h values? So keep our eyes on the prize, right? We want to find b and h. Well, we might not be able to find them exactly, but we could find when one of those values equals 0. So notice, for example, we could do when x equals 0, and that should be an easier one for us. So when x equals 0, what do we get? Well, when x equals 0, we have, plug that in, you get y minus 1 over c plus 7, the quantity squared, equals negative 2 over c plus 7 cubed times negative c. Okay, so we can add that over to the other side, and we get y equals, so you get negative times a negative makes it positive, so you get 2c over c plus 7, the quantity cubed, and then plus 1 over c plus 7, the quantity squared. So that can replace our h, and I'm actually going to give a little bit of room here. So 1/2, and then when we have b, we'll have some space here. And then h, we know is 2c over c plus 7, the quantity cubed, plus 1 over c plus 7, the quantity squared. All right, and the reason why is because we plugged in 0 for x, and notice that's what we called h, so x equals 0 right there. So that's how we were able to figure out that part. Now, the other scenario is when y equals 0. This might take a little bit more work, but not much. So when y equals 0, what happens to our equation? Remember, we're plugging it into the equation down below. So you get negative 1 over c plus 7, the quantity squared, equals negative 2 over c plus 7, the quantity cubed, and then we get x minus c. Alright, so we want to solve for x, so what happens here? Let's see. Okay, so we'll first divide by the negative 2 over c plus 7 cubed. So in a way to divide, we can notice negative and negative make a positive, so you get 1 over c plus 7 squared times, when we divide by this 2 over c plus 7 cubed, we should multiply by the reciprocal, so we get c plus 7 cubed over 2 equals x minus c. Okay? And so now, well, first actually, let's make this a little bit nicer. The c plus 7 squared, that would cancel off with the 2 of those 3 c plus 7. So we can write this as c plus 7 over 2 plus c equals x. And so now that must be our b value. So c plus 7 all over 2 plus c, that is our b, because this was when y equals 0. Okay, so we've worked with the problem, and so now we have everything in terms of c, which is good. So now we have a function a of c, so one single variable, that's good. We can work with that. So a of c equals, now let's try and freshen this up a little bit. And what do I mean by that? Well, so this c right here we could write as 2c over 2, right? And so then we can add those two together and we can get 3c plus 7 all over 2. Okay? In our next bit, notice we could write our last term to get a c plus 7 cubed. That means we would have to put an extra factor of c plus 7 on top. And so adding that to 2c, notice you get 3c plus 7 all over c plus 7 cubed once again. Okay, so this means that our a of c can be simplified a little bit. So a of c equals, what do we have? 1/2, and it looks like we have a, oh no, 1/4 actually, 1/4, and then it'd be 3c plus 7 squared all over c plus 7 cubed. Now one little comment here. We know that this is in the first quadrant, right? That's important. So what that tells us is c is greater than 0, right? So keep that in mind when we're actually going to be finding solutions. So I'm going to erase this part where we have when x equals 0 and y equals 0, just so I could fit in all this business. So we had this equation, we worked with it. So now where do we go from here? Okay. So let's take a look. So in order to maximize something, we need to find a prime of c. And so the equation we're going to work with is this a of c. And so that means a prime of c equals 1/4. We need to use the quotient rule, so we'll square the bottom. So that makes c plus 7. When you square a cube, that makes it to the 6th power. So we'll leave that c plus 7 cubed up top normally. Then we need to use our good old-fashioned power rule for a second, along with the chain rule. So this goes 2 times 3 times c plus 7. Then chain rule here, derivative of the inside. Derivative of 3c plus 7 is just 3. And so we're good with that part. And let me make a little more room here. And then this goes minus the derivative of the denominator, so it'll be 3c plus 7 squared. Notice derivative of the inside is 1, so I won't write that part. But then we have times of 3c plus 7 squared. Okay? So if we were to make this all out here, what do we get? We get a 4 in the denominator. We get a c plus 7 raised to the 6th power. Okay, what can we factor out? Notice we have a 3 as a factor of both terms, and let me kind of highlight that here. So you have a 3 here, a 3 right there. So we can pull out a 3. We have a c plus 7 squared, and a c plus 7 squared essentially sitting in here with an extra 1 power left over. But so, and then we have one factor of 3c plus 7. Okay, from each of those. So we could pull out the c plus 7 squared and the 3c plus 7. And then what are we left with? Well, we're left with a 2 times c plus 7 in the first case, minus, it'd be 3, oh no, we already factor out that, minus, let me put it in parentheses, 3c plus 7, sitting in that last case. So notice this thing equals, a simplified format for us is 4 times c plus 7 to the 6 in the denominator. You have the 3 c plus 7 squared. We have a 3c plus 7, and then this becomes, notice it's 2c plus 14 minus 3c minus 7. So that looks like we're going to have a minus c and we're going to have a positive 7, so it'll go 7 minus c sitting right there. Okay, so simplifying this on down, and remember, we're going to set this thing equal to 0 here is the main goal of this, and we're going to find other critical points too, but some of them won't be as important. So notice 0 equals, we'll have the c plus 7 squared will cancel off with the 6 and make a 4 down below. So 0 equals 3 times 3c plus 7 times 7 minus c all over c plus 7 raised to the 4th. So notice we have also the requirement that c is greater than 0. So when we actually do something like 3c plus 7 equals 0, notice we get c equals negative 7/3. That's not going to do anything for us, right? So that means it's not in that values that we want. But however, and we could do the same thing with c plus 7, but when we go 7 minus c equals 0, notice we get c equals 7, and that's a possible value. So we're going to have 7 sitting right here. Here's 0, and then this keeps on going. And so we have a, these are the c values, and then we have a prime of c. A prime of c equals 0 when we have 7, so we can plug in 1 into the derivative and see what happens. So notice we go plug in 1, we'll get what do we have here? Positive divided by a positive, so that makes this positive. And then plug in a number greater than 7, like 10. So notice you have a positive when you plug it into the 3c plus 7. And 7 minus 10 is negative, so positive times negative is negative, and the denominator is always positive. So at the end of the day, we get negative increasing to decreasing. That means this is the max occurring right there. And so that's useful for us. So now we need to find, notice it's looking for the area, right? So we got to take that c equals 7 and find our area equation once more. Well, our area equation, if you recall, it's back up here. So we locate that information. And now here's what we're going to do. We're going to plug in 7. So we get, and I'm going to put it up here just for kicks, 1/4. So we get 3 times 7 plus 7. That quantity squared all over 7 plus 7, the quantity cubed. Now I might be able to actually simplify this a little bit. Okay, so let's see. We have, that's 28 up top, so we have 28 squared divided by, okay, this will be very convenient. So yeah, we have 28 squared, and then we have a 4 times 14 cubed, right? So another way we can write this, I believe, we get 28 squared divided by, we could write this as 2 squared times 14 squared times 14. Okay, 2 squared times 14 squared would be, notice that's going to be 28 squared because we have the same thing, times 14. And 28 squared sitting right here. So our 28 squareds cancel. So our final answer for this whole thing, the maximum area and it doesn't have any units or anything like that. So the maximum area equals, this will be 1 over 14 units squared, or square units, because we're talking area. And that's it. So a lot of work, a little bit more intense problem because the derivatives were a little bit nastier. We had to do more algebra is essentially what you saw happening there. A lot of that was just algebra. But as soon as you work it out, it's the same process that we were using before. So let's work on one more, just so you can see. I wanted to give you ones that were a little bit more out there in terms of what's happening. Okay, so we have this kind of this nearsighted cow problem. This is in SESA Calculus Classic. There's all sorts of versions. Actually, this can come in handy if you're setting up a big screen TV in your house or something. Where do you set it, and where do you put your seat in order to maximize your viewing angle, essentially. Same thing with sitting at a movie theater. You can figure that out as well to maximize your viewing angle once again. And so what we have is a rectangular billboard, 8 feet in height, stands in a field so that its bottom is 6 feet above the ground. So let me just, we have an illustration, but I know it's kind of hard to see. So you have a billboard, right? And this billboard right here, we have this total length being 8 feet. Okay? And then we know that there's a skinny little post here, and then we know that this distance is 6 feet, okay, above the ground. And this, so this has to be ground level. Okay, a nearsighted cow with eye level at 4 feet. So I'm sure you will love this drawing of the cow right there. And I'll get a little, just to make it sure it's a cow there. So you have a cow. Now it says his eye level is at 4 feet. So I'll put the eye level here. I'm not saying this is to scale, but we know that this height right here is 4 feet. Okay. Above the ground stands X feet. So let's say this thing right here is X feet. And notice I could put that right up above where you see the 4 feet in same distance there. Express theta, the vertical angle subtended by the billboard at her eye, in terms of X. Okay, so we have this thing going on here, right? We're trying to maximize the viewing angle. That was supposed to be a straight line. Don't let your eyes fool you. Ugh. That's all sorts of nasty in terms of my angle drawing. Let's see here. Let's try this again. Okay, so there's what they're talking about being theta. Okay, that's what we want to maximize, and it wants theta in terms of X. So it's actually even telling us what it wants us to do here. So in order to do that, though, we're going to need a little bit more information. And so what I would do is, there's another triangle kind of lying here, and so let me kind of draw that. That's the elephant in the room here. So we have a triangle going from here to here. And that's the one that I'd really like to focus on real quick. So notice this distance is 2 feet from there, from the cow's eye level up to the billboard. That's important because we have a right triangle. Okay, so we can use that to our advantage. Let's say we added in this extra angle here. Let's call it alpha. Okay, so if we had taken the tangent of alpha plus theta, right, then that should equal, well, notice 8 plus 2 would be the opposite side, so that would be 10. And then the adjacent side of this angle altogether is x. Right? So notice then, from here we can take the arctangent of both sides, so you get alpha plus theta equals the arctangent, or tan inverse, whichever you want to write, of 10 over x. But that's not what it wants. It wants theta of x, right? And so we could do theta equals arctangent of 10 over x minus alpha. But that's still not what we want, because we have an alpha and we have an x. Those things vary depending upon where the cow is standing, right? So in order to do this, we're going to have to figure out another way to represent alpha. Okay, so we'll go back to the drawing board once more, and I'll bring out, I guess, green here for Kermit. So now, when I'm drawing this thing right here in green, what do we have? Well, we have another triangle that will give us this alpha. And notice what we can do is we could say the tangent of alpha equals, well, it'd be 2 over x, right? So that means theta, if we want to put it in terms of x, equals the arctangent of 10 over x, or tan inverse, you'll hear me say sometimes too, minus the arctangent of 2 over x. Let's go back to a more normal color here. So now we're ready to rock and roll. We could pretty much use this to try and find our optimum distance and angle as well. So theta prime, we take the derivative. This becomes 1 over 1 plus, we square what's in the inside of the arctangent, and then we multiply by the derivative. The derivative of 1 over x is negative 1 over x squared, but since you have a 10, it'll be 10 on top. So this is negative 10 over x squared. And then minus the derivative of the arctangent of 2 over x, that's 1 over 1 plus 2 over x, the quantity squared, times negative 2 over x squared. And in case you forgot, just a little FYI, the derivative of the arctangent of x happens to be 1 over 1 plus x squared. Okay? So we have that information, and that's where that kind of came from. We just basically use the chain rule on that. Now what do we want to do? We want to set this thing equal to 0. So we get 0 equals, now let's simplify this a little bit. We're going to have negative, and then it'll be 10 over, when we multiply x squared on the bottom, we'll get x squared, then you have plus 100 over x squared. The x squareds will cancel in that second term, so this is x squared plus 100. Minus and minus, so that makes plus. We'll have 2 over, now we'll take that x squared and multiply on through. That'll get us x squared plus, it'll be 4 over x squared. The x squareds will cancel, and so you're left with that. So now for solving this thing, we get 10 over x squared plus 100 equals 2 over x squared plus 4. This allows us, well, rather than cross multiply, I'll divide both sides by 2, and so we'll make 5, but then we'll cross multiply. So 5, and then it goes times x squared plus 4. If you get lost in that step, let me know. Okay, 5 over x squared plus 4 times x squared plus 100. Basically, we divided by 2 on both sides first. That'll cancel off the 2 on the right hand side, and 10 divided by 2 is 5. And then we cross multiply because we have 1 on the numerator on the right hand side. So we get x squared plus 100. Okay, so this isn't so bad. So we have 5 x squared plus 20 equals, well, equals 100. So that means 5x squared if we subtract 20. Yeah, well, I'll do that. 5x squared plus 20 equals x squared plus 100. So that means 4x squared equals 80. In other words, x squared equals 20. And there's one thing to take note of. X has to be greater than 0. Well, greater than or equal to. So if that's the case, that means x has to be positive square root of 20. Now just to double check and make sure this works out nicely, we'll have to plug in numbers. So we start at 0, and we have square root of 20 sitting right here. And hopefully we can see that still. If not, I can fix that real quick. There we go. Hopefully that'll look a little better where you can see it. So now, taking a look at that, we need to plug in values for our x and our theta prime of x. Okay, so taking a look and pick a number between 0 and square root of 20, I'd suggest 1. Notice that gives us negative 10 over 101, and that's 2 over 101, so that means it's negative. Right? Wait, did I do that right? Hold on one second. I gotta make sure. I'm sorry. I said negative 10 over 101 and 2 over 101. Negative 10 over 101 and 2 over 5. Obviously 2/5 is greater than negative 10 over 101 because that's going to be, so that's actually positive. And now take a number bigger. Let's do 100. If we do that, we get 100 squared, and so you'll get the negative 10. When we do the 100 squared and the 2 over that 100 squared plus 4, that won't quite cut it for us anymore. So that'll be negative on that side. So that means we're increasing to decreasing. So that means a max. And so just so you can see it, theta of x equals, we had arctangent of 10 over x minus arctangent of 2 over x, and theta is maximized when x sub 0 equals the square root of 20. Questions on those? So those are the optimization ones, and we'll get moving forward into Riemann sums now. Those can be tricky, so wanted to make sure that we had those down. So using the graph of 6 plus cosine of x for 0 less than or equal to x less than or equal to 3 pi, list the following quantities in increasing order. So let's actually, first things first, let's draw this graph as best we can. Okay, so we have this graph going here. Let's say we start with 6 right here, and that means, I'm not saying this is to scale whatsoever, so we'll put 5 here and 7 here. So what happens with cosine if we go 6 plus cosine of x? Notice cosine of x, we just shifted that graph up 6 units. So we have pi over 2 pi, 3 pi over 2, 2 pi, we have 5 pi over 2, and then we'll have 3 pi. That's how far we want to go. Okay, so let's kind of check this out. So we start our graph of cosine x plus 6 at 7, right? Because you plug in 0, you get 1. Cosine of pi over 2 is 0, so that means we'll be at 6 at that point. So I'll put a big mark here, and we get a curve that kind of goes like this. Okay, so now moving forward from there, what happens? Well, so then we want to try and go from pi over 2 to pi. Notice cosine of pi is -1, and so we'll put that in right there. We get this smooth looking curve just like so. Cosine of 3 pi over 2 is going to be 0 once again, so you'd get 6 at that point. And then cosine of 2 pi, we're back made full circle if we're using the unit circle, and so we go back right to that 2 pi part. Cosine of 5 pi over 2 is 0, so we're back to this part. And then cosine of 3 pi would be -1, so we get this value. Okay, so now I'm going to start in red, and what we'll do is the left sum with n equals 3 subdivisions. Okay, so if we have 3 subdivisions, notice that goes 3 pi minus 0 divided by 3. Our intervals should be at pi units. Okay, so every pi we're going to mark. So we'll start at 0, we'll mark here, we'll mark here, we'll mark here, and we'll mark here. Okay, now it says we want to use a left sum, so here's the way to do it. You start from that leftmost interval, so we're going here, and we're going to draw it all the way until we reach pi. Right? Then from here, we're going to go from pi until we reach 2 pi. And then from here, we're going to go from 2 pi until we reach 3 pi. Okay, so let's take a look at the area. Notice you have 2 overestimates. Now, this will be, I'll admit, for right now, we'll actually learn a better method to determine is this an overestimate or an underestimate. But there's only one portion of the graph that we've kind of underestimated, and that would be, I'll shade that part in, right about here. Okay, so that's actually our underestimate. Now, the rest are overestimates. So we have an overestimate on this portion and an overestimate on this portion. Now, I'm not saying the graph is necessarily to scale, but what it does seem like as of right now, it seems like B must be larger than, what does A represent? A represents the whole area down below. So, and so let me write this. Overestimate in those two portions, and this portion would be the underestimate. Versus the actual integral, what we're looking at, the actual integral would be all this shaded underneath that curve over that interval. So what that tells us is that B seems to be greater than A. The main one, though, I want us to compare is B and C. And so I will use orange just for kicks here. So the orange one, what does that mean with right sum? So we still have our points marked, but now we're going to start working from the right and go backwards. So we'll go here, and we're going to go all the way to 2 pi. And so this is the area that we're looking at. Okay, so notice you're missing a whole bunch up above. The next part, though, we're going to go from here all the way until we reach pi. Oh, that should be the same height, actually. But so you have a little bit extra, right? So you have this along with what's below the curve. So that's the overestimate in that case. But we had an underestimate before. And then from pi, our third interval, going back to 0, notice we just have this portion. So this is, once again, we have underestimates. So you have 2 underestimates and 1 overestimate. That doesn't mean it would always be, I mean, you could have a greater overestimate, but the symmetry here, things work out nicely. So that means, if you look too, our overestimate only occurs in the one spot, and the rest of the curve we're missing. So it seems like this is even smaller than A. So this is what we have. C is less than A is less than B. So we're looking at areas is the main thing. It's all focused on areas. So as long as you're working with those, you're good to go. Okay, questions on that? If not, we'll move forward to our next one. We have the graph of a function g is given below, and then we want to estimate this integral from -3 to 3 using 6 subintervals with right endpoints, left endpoints, and midpoints. So we'll do that. So the interval length, we'll take the bounds, right? So we'll go 3 minus -3, and then we're going to divide that by the number of intervals, which is 6. So each of our intervals, notice that 6 over 6, which is just 1. Oh, that's convenient. So, and we have 1 being every 2 units on our grid, so that's not going to be too bad either. And so this will actually be an approximation. I'll use pink to start here. So we'll start from the right endpoint. Oop. Okay, so that should be 3 right there, and we want to go over 1 unit. This is right endpoint first. So there's our area of our first rectangle. Okay. Then we got to go from here. We got to go to the curve. So we'll go from here, go over 1 unit. There's our area of our second rectangle. Now notice this is below the x-axis, so this is going to be negative. Then the third one, we're using right endpoint, so we'll go from here to here. So we got 3 rectangles so far. Okay. Our next one, same thing. And then our next one, we want to draw another. And then finally, last but certainly not least, we'll draw on this. Oh, I went way too high there. Getting a little ahead of myself. So we have this one. Everything stops at the x-axis. But so I was going on to this next portion. Sorry about that. And we draw on our final interval. So now we just need to figure out the area of all these rectangles. And remember, above the x-axis is positive, below the x-axis is negative. Well, so this is 1 unit by 1 unit. So that means this area right here is 1. Versus this next one, it would be -1/2 because we're below the x-axis. And so same thing with the next couple. If you look, so we have 3 and 1, so 3 and 1, so this would make -3. 3 and 1, and so what do I mean when I say in 3 and 1? 1 is that length, and then our height, well, I said 3, I'm sorry, -3/2, I should say. So yeah, should be a little bit more careful there. So it's -3/2 for our distance. This one's -3/2. This one's -1/2. And then our last one, we go up 1, we go up 2, it looks like 2.5. So 2.5 or 5/2. So now we have all our areas. Here's what we do. We just add them up. So you go 1 minus 1/2 minus 3/2 minus 3/2 minus 1/2 and then plus 5/2. So let's see, what does that make? So we have -1/2 and -1/2 makes -1. And then we have -6/2, which is -3. So that's -4 right there. And then we have 3.5. So this whole thing was 0.5 for all those. Questions on that? So now let's try our left end point. So we're going to start from our left end. Remember, we're making 6 of these intervals. Okay, so let's just mark the intervals parts. So you go, here is our starting point, and we want to go 1 unit at a time. And so a slightly different approach than what you've seen on the right end point. Just want you to see the variations of what we're doing here. And that should be our last one since we have 6. Okay, so our rectangles look like this. So we start from the left hand side. Everywhere you see a dot, you're going to draw a rectangle out to the right until it hits the x-axis. So you might have to go back up, like in this case, or before we were going downward after we touched that point. And so notice this time we're doubling up down below. Okay, let's see the difference. Okay, so notice this is our first one is 1 by, and you can calculate the areas if you want to write out each part, like so 1, and then this is 1. So our first area is 2, our second area is 1. Right. Our third area, notice we're only going down, so this is -1/2, and then we have 1. So this is -1/2. Our next one, we get -3/2, get -3/2 again, and then we get -3/2 once more. So, or -1/2, I'm sorry, once more. So adding all these up, notice we get 2 plus 1. Then it goes -1/2, -3/2, -3/2, and then -1/2. Okay, so taking a look at that, what do we actually have? Well, in our case then, what is that, 3, and then we get -3, and then another -1. So that should be, yeah, -3, so -1. Let me double check. I think the previous one I might have wanted to write -0.5. Hold on. So it was -3, -4. Yeah, so the previous one was actually, I don't know if I said it, -0.5. So here, let me rewrite that. I just made a mistake arithmetic wise. -0.5 for the first one. Okay, so now we're rocking and rolling. Last but certainly not least, this last one. So we've done the right endpoints, we've done the left endpoints. Now we're going to finish up with finding the midpoints. And I'll actually use black this time. Okay, so now for the midpoint one. I don't want to start at the left endpoint, I don't want to start at the right endpoint, so I got to start at like halfway between each interval. So notice our interval, if we started over here and finished over here, the midpoint would be somewhere right in, I'll put this asterisk mark, so I got to go to the curve where that asterisk mark is. And then I'm going to basically be jumping 1 unit at a time. So go here, there. So there will be some tricky values coming in here. Okay, and so now we want to have this kind of balancing act. I know it's not going to be right on the mark, but I'm going to be using kind of a shortcut just to make it look a little nicer. So in the other one there, notice the rectangle is 0, so we don't have to worry about that. Next one, we have a rectangle right here. This is our tricky one. And then we have this rectangle right here. And then finally, last but certainly not least, our rectangle right about there. Okay, so notice on this one, our height is 1.5, and then our width is 1, so I'll just put 1.5. This one is 0, so there's nothing to that one. This one's actually going to be -1. Now, for our next bit, let's say this is a -1.75. That means, with this being our width, being 1, this whole thing is -1.75. And then we have another -1, and then we have a positive 1/2 to finish off, or 0.5. So notice we can write 1.5, and I'm going to actually write this one. Something I usually do is actually write where I put all the positives up top, then I just subtract off all the negatives. So we get -1, -1.75, and then minus another 1. And then that's going to be easier for us to kind of see adding up. So notice you get 2 right here. You get a negative and a negative, so that's -2. And then this little bit is -1.75. So you get the 2 and -2 cancel, and we're left with -1.75. So you can see the difference between the 3. Okay, that's the main moral of the story that we're looking for. Now, moving forward to our next one, so we have a task here. It says your task is to estimate how far an object traveled during the time interval 0 less than or equal to t less than or equal to 8, but you only have the following data about the velocity of the object. So you have the time for those essentially 1 second intervals, and then you have the velocity in feet per second, right? So, and the velocities range, as you can see in the graph, is what they're getting at. So to get an idea of what the velocity function might look like, it says you can pick up the black pen and plot the data points and then put curves in there. The curves aren't necessarily what we're going to be focused on, but the points themselves. Now it says you decide to use a left endpoint Riemann sum to estimate the total displacement, right? So you pick up a blue pen and draw rectangles, and basically that's what they're illustrating here. Okay. And it says by using the left endpoint Riemann sum as an approximation, you are assuming that the actual velocity is approximately constant on each 1 second interval, and that is true. Okay, so we're going to have some overestimate or underestimate most likely involved. But with this assumption, it wants us to make the calculation of displacement and total distance traveled. So displacement, what that talks about is if you have a starting point, how far are you from the starting point when you finish, right? And you have to have some orientation of positive and negative. Distance, however, is exactly what we're doing. How long do we go for the whole trip? So that's what we'll talk about. And I think that's 1 right here. So this is, oh yeah, since that's -1, this is 1.0. So notice we have 1 by 1. So this is 1 unit right here. Okay, and then in our next one we have 4 by 1, so that means we have a 4 sitting right here. Okay, for our next bit we have -2, since we've gone down 2 units, and next one is -1. Notice since each of these have width 1, these are easy calculations. So the next one is -4, next one is -3, -1, and -3 for our values. So we can actually find the displacement. That's not too bad. So displacement, here's what we're going to do. We're going to take 1 plus 4, and then we go -2, -1, -4, -3, -1, -3. Okay? And just to make life a little easier, let's try and cancel things out. We can. So I should write total displacement. So 1 plus 4, then the 4 will cancel off with that -4, so we get -2, minus 3, minus 3, so that's minus 8, minus 9. So our total displacement is negative 9, and then our units are feet per second, so that means it's negative 9 feet. Now the total distance, however, remember we're looking for how far we traveled, not how far we're from our starting point. So that means each of these down below, for when it comes to distance, are positive, right? So basically we're taking the absolute value of all those. So here's what we get. We'll get 1 plus 4 plus 2 plus 1 plus 4 plus 3 plus 1 plus 3. That's the difference between distance and displacement. So now, distance. So, and to give you an example, for those of you who have like fitness trackers or something, say you have your Fitbit or Garmin or Apple Watch tracking you, right? It tells you distance traveled essentially after you've done a run, but most of the times you start at one place and you finish where you started a lot of times. So your displacement will be 0, but your distance travel will be what appeared on your watch for that little exercise, right? So there's the difference between displacement and distance, to give you an idea. So now in this case, what do we have? We have 5, 7, 8, 12, 15, 16, 19. So it looks like 19 feet according to this. Okay. Alright, so we'll keep on moving along then. I don't see any questions popping up thus far. So we want to use the graph of f of x in the figure to find the following integrals. So now, a little bit more interesting, we have the integral from negative 4 to 0. So that should be our area going on right there. So a little bit more fun now. So what I'll actually do is break this up into a couple different pieces. So we're looking for this. So what do we have? Well, area, remember, is 1/2 base times height when we're a triangle. So our height, it looks like, is -1. So this is, so we have 1, and then we have our -1. And this is 1/2 base times height, so that should be -1/2. Okay, in a similar manner, we can get this distance here from -3 to -1 is 2. And then we drop down -1 once again. So this should be -2 appearing there. And then this last piece is the same, it's symmetric to the other, so we get -1/2. So for our integral from -4 to 0, we get -1/2 minus 2 and -1/2. So now we've gone away from the Riemann integrals. We were actually calculating the area because we know those shapes. So we get what? This is -3 overall. Okay. And so now from -4 to 6, there's something beautiful that happens. So notice though, you have basically the same exact shape, right? Appearing as a positive. So this is +1/2, this is +2, and this is +1/2. So what you can actually do with integrals, there's something kind of neat here. You can break it up into separate integrals. So we can do -4 to 4 of f of x dx, and then add that for our leaving off point. So from 4 to 6 of f of x dx. Now the thing that we just realized, since we have the negative and positive version, this thing goes to 0, right? And it said the blue shaded area in the graph has area what we'll call A. So that area from 4 to 6 represented, that is A. Now it's going to be a negative number of some sort, but so we have A. And so that is our final answer for this. It's just A. And the thing is, we can just break up the integrals, cancel off what we need to, and keep on going from there. Since we're summing area along, we can break it up at any point in time. Alright, so moving forward, suppose the region on the left in the figure has area with the blue shading, has area as 36. So notice the blue is below the x-axis, so that means technically, even though the area is 36, that means this is -36 from the standpoint of what we're plugging into an integral. And the region on the right, has area 12. So this would be plus 12, so I'll just put 12 right there. Using the graph, we want to figure out, okay, and just so you can see it a little bit better, that's A, and that's B, and then hopefully you can see C just fine there. So the integral from A to B, it's just that area shaded in, that's going to be negative 36. The integral from B to C would be just 12. When we go from A to C, it's just the same idea of what we just used. All we need to do is just break it up at B, because we know the integral from A to B, and we know the integral from B to C. And so what we get is you get negative 36 plus 12, which is 24, I believe, with a negative symbol in front, so negative 24. Okay, so now the last trick, we can do the same thing with absolute value. Okay, so this can be the integral from A to B of the absolute value of f of x dx plus the integral from B to C of the absolute value of f of x dx. So notice when you take a look at this, the integral from B to C, that's already above the x-axis, so everything's hunky-dory. That's still going to remain 12. But what happens with this other part right here is we get this negative values always have to turn positive. So everything that you see up here is going to be above the x-axis now. So you just reflect it over the x-axis. So instead of negative 36, it's going to be positive 36. So our answer is just going to be 36 plus 12, which is equal to 48, right? Questions on that? So now that you've seen all those working together, let's try and work our own here. You have the graph of 4x minus 1 on the integral from 0 to 4. Okay, so notice this is always going to be positive. That's not too bad. Another way to write that too, you could do 4 and then that's x minus 1/4 essentially, right? If we said this is f of x. So what does that do? That shifts the graph to the right 1/4 unit. So let's say we have 1/4 unit. I'm not saying this is going to be to scale. And when we plug in 0, notice we're going to get positive 1 because you get negative 1. Absolute value of that is positive 1. So we'll say, I'm not saying this is to scale once again. And then when we plug in 4, notice we're going to get 15. Let's say 4 is just way down here, and then we'll have 15 sitting up here. Once again, this is not to scale whatsoever, but we know what the graph of absolute value looks like. It's a V, right? Now granted it would extend further and further, but that's okay. We got our V, and now all we need to do is start getting our area, right? So what this becomes is two nice shapes. We need to calculate the area of these two shapes. So notice this is 1/2 base times height. So 1/2 times 1/4 times 1. So that makes 1/8 is our area there. And now we got to figure out, okay, so what is this? Well, this would be 16 over 4, which makes 15 over 4 when we subtract off that 1. So and the way we got that was we took 4 is 16 over 4 minus 1 over 4. We just subtract those two. And then our height is 15. So notice this is 1/2 our base, which is 15 over 4, and then times our height, which is 15. Okay, so this makes, notice we'll get 1/8 plus, that would be 15 squared over 8. And so you can do yeah, actually be fine with you leaving them like this. 15 squared plus 1 over 8. That is a fine final answer when it comes down to it. Or you can multiply out 15 squared and get your final answer and simplify if you wish. But at the end of the day, notice we're able to get those integrals. So hopefully that lets you see in terms of what the area is, and you could see in some of the previous problems as well how we played with the area and that whole song and dance. You know, just seeing how we're trying to highlight and cancel things out if possible, or just try and get it into a common shape that we know. That's what we're going to be building to, and then soon enough we're going to start seeing what's called antiderivatives. That's the main moral of the story that we're going to be getting to. So hope all went well today. If you have any questions, please do not hesitate to ask and post them in that YouTube live discussion board. So y'all have a good one.